In section 4, we look at a couple of examples of motion in a plane. In section 1, we looked at motion along a straight line, motion in one dimension. Now, armed with our vast knowledge of how to deal with vectors, we can consider, well, for example, instead of taking a ball and throwing it straight up in the air, which makes for kind of a boring baseball game, you can throw it at an angle. And the ball would follow a parabolic arc through the air. And so it's moving in a plane instead of along a straight line. The two examples we're going to look at are the one I just mentioned, the motion of a projectile. Projectile is something which has been projected, thrown, in other words. Could be a baseball, except realistically, nobody in the middle of a baseball game sits down with a pad and a pencil and calculates where the ball is going to go. You just sort of get a feel for it. The ones who are really careful, you know, have all the calculations and everything, that would be the military when firing artillery. Now, the thing is, we're just going to consider the frictionless case, which is not really very realistic for an artillery shell. They travel at, you know, a couple times the speed of sound. And at very high speeds like that, air drag is very definitely significant. But projectiles, projectile problems which take air drag into account are a topic for an upper division course. You can't do that with students who haven't taken a course in differential equations yet. So we'll look at the frictionless case anyhow to kind of introduce the subject. And, you know, it's just good exercise in working with vectors. And it does work quite well with things at low speeds, as you'll see, for example, in this week's lab. So the trick with dealing, well, with vectors in general, whether it was a box sliding down a ramp like last week, or a projectile like this week, or if you're doing some sort of momentum analysis of a collision like a couple of weeks in the future, it's all the same in the sense that you have to think in terms of components. These things are all vectors, and the great majority of the time, anyhow, the best way to deal with vectors is in terms of components. So what does that mean in the case of a projectile? Well, like it says here in this opening paragraph, imagine that you're in some huge auditorium, you know, where they might play hockey or something like that, and except you're the only one there today, and you throw a ball. So imagine that way up far above you on the ceiling, there's a spotlight shining downward, and that makes a shadow for the ball going along the floor underneath it. Also imagine that there is a very tall wall right behind you, and far off in the distance in front of you is another spotlight, so that there's a shadow of this ball also going up the wall and later coming back down. When I talk about the x components of the ball's position, velocity, and acceleration, I'm talking about the position, velocity, and acceleration of that shadow on the floor. And when I talk about the y components of those things, I'm talking about the shadow on the wall, okay? Each of those shadows is an example of one-dimensional motion, okay? You just go right back to section 1, and each of those shadows obeys that little group of 5 equations that you used for many of the homework problems in that assignment, the one where the lady fell off the building and so forth, okay? So that's basically the whole trick to it. The X and Y components behave independently of each other. You can write an equation for each shadow, and between the two equations, you can solve for what you're looking for. Or on a good day, maybe you only need one equation, but quite often you'd have to get involved with both. So how does each of those sets of components behave? A little bit higher, I think. Maybe a little bit closer. Should have done this before I started recording. Yeah, that's probably about right there. Okay, so let's think of this as an F equals MA problem. And, well, put a title over it. Projectiles. Anytime you do any kind of F equals MA problem, start with the diagram. So if you've thrown a tennis ball to a friend that's sitting a short distance away from you, that wouldn't be going very fast at all. Air drag would be extremely small. Here's the free body diagram of that ball. That's it, one force. If we're assuming friction is small enough to ignore, then the only thing pushing or pulling on this ball is the Earth's gravity. This would be, of course, after it leaves your hand, okay? While it's still in your hand, it's not a projectile yet. So apply Newton's laws. Or Newton's second law. I guess there's just one of those. From last week, the net force in the x direction is proportional to the x component of the acceleration, and the y component of the net force is proportional to AY. And so you go to the diagram. Every place there's a horizontal arrow on this picture, that's one of the terms in this summation. There are no horizontal arrows on that picture, so it gets a big fat 0. Now, in the case where friction is present, like if the ball was traveling in that direction, friction always opposes motion. The air drag would be in the direction opposite of its motion. That air drag would have an x component that makes the x component gradually slow down as time passes. That's if there's air drag. But like I said, we're not going to get into that. That's beyond the level of this course. So in the frictionless case, nothing. Solving for AX is probably not the most challenging piece of algebra I'm ever going to throw at you. So you come to the conclusion that the shadow on the floor maintains a constant velocity, okay? If that shadow is going 12 miles an hour, at the moment it leaves your hand, that shadow will continue to move 12 miles an hour until your friend catches it. No acceleration horizontally. Now, what about the shadow on the wall? Well, here we do have a force. If we say that, up is positive, then minus mg is equal to m times ay. Divide both sides by m, and it cancels out. And the conclusion here is that the shadow on the wall behaves exactly like a ball that's been thrown right straight up, like came up once or twice back in section 1, okay? If you throw a ball at an angle and somebody else throws a ball straight up at the same speed as the y component of the one you threw, the shadow and the real ball are going to stay right next to each other as they go up and come back down. So the shadow behaves exactly like, well, the tennis ball is a freely falling object, okay? And so its vertical shadow behaves like one. So that's the explanation for what's underlined here on the handout. The x component has a constant velocity. The y component has a constant acceleration. And you just keep that in mind while using the equations from section 1. So a few examples. First one, let's lift the handout. Okay. Section 4, example 1. The kind of things students hate. Well, actually, I suppose there are several kinds of things that students hate, but one of them is problems that are full of letters instead of having any numbers in them. You can give the exact same question where, you know, if that said 41 degrees and that said 30 meters per second and so on, everyone would be like, okay, yeah, that's not so bad. And you just change it over so that it's a theta and a V, and they're like crying and carrying on. And but you know, it's often good to solve questions in a more general form like this, because then if somebody comes along the next day and says, well, okay, what if you throw it now at 36 degrees? Well, if you've just solved a problem full of numbers, you have to do it all over again. Whereas if you did it in a more general way like this, you just stick the 36 degrees in the result that you determined. So it's a good thing to be able to do. And it goes like this. I guess I want it about there. Seems a little further to my left than I usually put it, but maybe not. Well, if you're going to think in terms of components, maybe a good place to start is to get all the components. Now, the components of the acceleration, 0 and minus g, you already know those. The initial velocity, we should do something with that. The question says the initial velocity is vi. And when it first leaves your hand, it's moving in a direction theta I, measured as usual counterclockwise from the x-axis. So the initial x component, as usual, that's the hypotenuse times the cosine, because this is the adjacent side of the triangle. And similarly, the y component will be the same sort of thing with the sine. Okay, well, I'm going to let that sit there for a few lines of calculations and get back to it. In the meantime, from section 1, maybe you remember, or if you don't, that's why you have a formula sheet. But maybe you remember that one of the equations back in section 1 said this. Let's apply that to each of those two shadows I was talking about. In the y direction, take that equation, stick a bunch of y's all over everything to indicate you're talking about the y components, except of course for the time. Time is a scalar. It does not have components. So the time is just the time, how much time the ball is in the air. And similarly, take the same equation, stick a bunch of x's all over it to indicate you're talking about the x components, and that'll be for the shadow on the floor. So this is the thing the question asks for. Maybe I should put a little sketch over here in the corner. We're going to assume that the ball was thrown from the origin, because you can define the origin to be any place you want, and it's convenient that way. So that the thing is thrown there, and it goes up in the air, and it comes back down over here. We're assuming, well, we don't have to assume anything. It says right in the question, it's fired over level land. So maybe this is the Navy shooting the guns, you know, because the ocean is pretty level. Anyhow, the thing lands at the same elevation that it was fired from. And the question is how far away? So that would be this, which is sitting right there. So if we can fill in for all these other things, the 1/2 AT squared term is 0, okay? Common mistake. And again, think in terms of components, okay? You need to separate the x's and the y's in your mind, or maybe even like make a little table. I'll do that in the next example and get it all laid out in paper. But common mistake, somebody sticks oh, it's a free falling object. The acceleration is 9.8 downward. Well, remember, back over here, the y component is 9.8 downward. If you're talking about the x components, there isn't any downward. X means right or left. There is no acceleration to the right or left. So this one is 9.8. That one is 0. So the 1/2 AT squared term doesn't even exist. It's just distance equals speed times time, because it's moving at a constant speed. Meters per second times seconds gives you meters. So I've got this to stick in for Vx. If we only knew the time. Well, you can get the time out of this one. So that's the strategy here. By looking at the y components, you can get something. If we had numbers for all of this, you'd find how many seconds it's in the air. As it is, we'll just get a formula for it, an expression. And then once you know the time, you stick it in there and it's good. So what I'm going to do for the next few lines is I'm just going to keep writing v initial y because it's quicker and easier than writing vi sine theta I. But keep in mind that this is supposed to be something we know, okay? Filling in other things that we know. This one bothers people fairly often. Delta y equals 0. The reason why, well, delta anything means final minus initial. And y initial is there. The shadow goes up, the shadow comes back down. Y final is right there, okay? So y final equals y initial. Y final equals y initial because the question says it's level land. Displacement is not the same thing as distance traveled, okay? I mean, maybe this ball goes up 12 feet and comes back down 12 feet. So the shadow on the wall has traveled a total distance of 24 feet. And that is entirely beside the point. Displacement is not the total distance covered. Displacement is how far from where you started to where you ended up. And the shadow on the wall ends up in exactly the same place that it started. As I said, eventually I'll fill in this for v initial y, but for the time being, it seems a little quicker just to write that. The y component of the acceleration is equal to minus g. I have filled that in. So I have kind of run out of space there. Guess it's time. Yeah, it's a little crooked, but it'll work. So taking let's see, can I get everything in here at once? Maybe. Okay. It's a quadratic. It's a second degree equation. Okay. One that's pretty straightforward to factor. We can factor a t out of that. Kind of like that. Like all good little quadratics, this one has two solutions. There are two values of t which make the equation true. That's because there are two different times at which delta y is equal to 0, okay? When the ball first, well, I guess we're talking about the shadow. When the shadow first left the ground, delta y equaled 0, and also when it returned to ground level. So two different times where delta y equals 0. This factor gives you one of them. T equals 0 is one of the solutions. That's when it left the ground. Or the other mathematically correct solution comes from setting the other factor equal to 0. Well, this is the one we care about, okay? We want to know where it lands when it returns to the ground. And I've kind of gone off the edge there. So equation has two roots. One of them is when delta y equaled 0 as it was leaving the ground. The other one is when delta y equaled 0 when it returns to the ground. Solving this for t, I sort of done a couple of things at once there because I'm running out of space. But I added this to both sides, and then I multiplied both sides by 2, and then I divided both sides by g. So a few lines of elementary algebra gets you from there to there. And that is the root that we care about. So now, from the x equation, the initial x, it's off the edge here. Remember that? X component of the initial velocity. The initial cosine of theta. So the thing from the triangle here goes in for v initial x. And for the time, the thing I circled over there, v initial y, was the sine component. Maybe I should do it this way. Okay, so from there to there, that's the time. Copy the 2, copy the g, and v initial y is hypotenuse times the sine. V initial x is hypotenuse times cosine. And now a few lines of algebra to kind of clean that up. For example, there are 2 v initials in there that we can combine into a v initial squared. And kind of rearranging the order on the rest of it. Well, there are usually a couple of people in the class who are on their toes enough to recognize the quantity in parentheses as being one of those trig identities that they, well, when I went to school, that was in 11th grade math, we learned that sort of thing. I think I took math the next period right after flint napping. But yeah, a few things have changed since then, but it might very well still be 11th grade math where you do trig identities. Anyhow, regardless of that, whatever did happen to all the mammoths anyhow? Sine of 2 theta is what's equal to the thing in parentheses. So substituting that in, we get to the thing with the box around it, which is referred to as the horizontal range of a projectile. So instead of delta x, I'm going to call it R for range. And it's equal to the square of the initial velocity. Well, maybe I should call it the initial speed. And the direction of the initial velocity is theta I. So, if you know how far away your target is, and you know the muzzle speed of your gun, which you could control by how much powder you put in it. Of course, you know that G is 9.8. You could use this to determine what angle to tilt it to fire the gun so that the projectile comes down in the spot you want it to, assuming it's a frictionless situation, of course. Well, first shot would probably come down maybe a little short of the target because of the air drag, and then well, let's put it up another degree and see what happens. But and then, you know, in the real world, there's crosswinds and all sorts of complicating factors. But I should probably emphasize that even in a perfectly frictionless world, this is for a target at the same level as the gun only. That was explicitly built in right there, okay? If delta y does not equal 0, then of course everything that follows from this is wrong. So if you're somebody who's sitting out there kind of snoozing along through class, and then it's like, he got to the part with the box around it, and you write that down, well, like I said, this is just a special case. Now, the next problem, I'll put the camera back over by the handout in a moment. The next problem is almost exactly like this one, except this is not 0. So if you understood the process I went through, then you're ready to do, well, like there's a problem in the homework, if I remember right, where a gun is fired horizontally. Same thing in the next example that I'm going to run through, actually. And you're asked how far down, you know, if it's aimed right directly at the center of the target, how far below the center of the target does the bullet actually hit? Because it drops as it's flying along. And you would do that problem exactly the way I did this one, with a few minor details being different. This 0 here being one of those minor details. You don't know this. In the case of the one in the homework, delta y is the thing you're looking for. You don't know it's 0. It's the thing you're trying to calculate. So anyhow, the point is that the point of all of this is how I did it. The answer is just sort of an incidental special case. If you happen to be talking about firing a gun across the ocean, yeah, this will work pretty well. On the other hand, if you're shooting at somebody that's sitting up on top of a hill or something, this is not going to work. Okay, so it's a special case. Don't use it outside of that special case. So the next example, maybe you'll like a little better. It has numbers in it. Number 2. We've got something kind of like you might see in a movie with Johnny Depp in it or something like that. Our hero, the pirate, I'm not quite sure how pirates got to be good guys, but that seems to be the way it works now. Our hero, the pirate, is down here in this ship, and the bad guys up here in the fort are shooting at them, but of course, bad guys are always lousy shots. And yeah, some cannonballs will tear through some sails for dramatic effect, but our hero will be okay. Anyhow, this gun up here fires cannonballs at 100 meters per second, which is really pretty slow for a cannon, but well, you know, it's like the year 1521 or something like that. That's probably even a little on the slow side for 1521, but well, it's a nice round number. I like the way things came out. Anyhow, if the muzzle of the gun happens to be exactly above this completely vertical cliff, the question is, how far from the base of the cliff does the projectile come down? If we knew exactly where that ship was, we'd be calculating whether our hero's ship gets a hole punched through it or whether it misses. So, as I said, a minor variation on the process that I just went through. That's about where I want that. What might be helpful, because remember I said earlier, where people go astray is they start mixing up X and Y components and things like that. So just like in section 1, I told you maybe it's a good idea to lay out your given information and what you're trying to find right on paper. The trick to solving a big problem is breaking it down into lots of little problems. And the first little problem is figuring out just what the given information is and what you're looking for. So in a two-dimensional case like this, maybe it'd be helpful to lay it out in a table, something like this. X component, Y component, and the thing that the question either tells us or asks about is the cannonball's final position. It tells us its initial velocity, and the question doesn't come right out and explicitly say so, but a frictionless projectile is a freely falling object, so we know about its acceleration also. Final position, the X component. How far from the base of the cliff does the cannonball come down? Okay, well, the water's horizontal. So how far from the base of the cliff, measured along the water, that would be the x component. The ball having been fired from directly above the base of the cliff. For the y component, the thing that was 0 when I did the previous example, negative 120 meters, assuming that up is positive. The cannonball, somehow I feel like I shouldn't use the word lands when it's coming down in water, not land. But whatever is the right word for when it stops flying around, it does that 120 meters below the point where it was fired. Initial velocity, maybe a little arrow, a little diagram would be helpful. That's a sketch of the velocity vector at the moment that it emerges from the gun. Okay, when the cannonball comes out of the gun. It's perfectly horizontal. Okay, it's right on the x-axis. So the x component of that would be 100 meters per second. The y component, well, it doesn't go up or down at all. That's 0. So multiply 100 times the sine and cosine of 0 degrees if you want to. But for me anyhow, you can get this just by looking at the sketch. It's right on the x-axis, so it's its own x component. It's a similar story with the acceleration vector. And I may have drawn it a little crooked, but that's supposed to point right straight down. The horizontal component of a vertical vector would be 0. And its y component is that. And as usual, you have the choice. You could have called down positive instead of up, in which case you wouldn't have these minus signs to deal with here. That's a completely arbitrary choice. Today I wasn't in the mood, so I said up was positive. Okay, it's going to be just like I did before. We will use the y components to find out how much time this thing is in the air. Once I know the time, then I can find delta x from that. So in the y direction, same thing I wrote in the other example. When you fill stuff into that equation, you stick to what's in the y column. So negative 120 meters for y. And just to repeat myself, because if I repeat myself enough, maybe somebody will remember. Typical mistake in this kind of problem, somebody says, I need the initial velocity. The initial velocity was 100 meters per second, and they put a 0 in there. What x components do not belong in the y equation. Okay, the y component of the initial velocity is 0 because it was fired horizontally. Think in terms of components. It's not just the acceleration, and it's not just the initial velocity. What is the y component of that? Multiply through by -1, and the minus signs cancel each other. and divide and then take the square root. And this cannonball is airborne for just a little under 5 seconds. Once you know that, another way of coming up with this, I mean, I showed it before, is coming from this equation here with AY set equal to 0, or I'm sorry, AX equal to 0. Another way of looking at it is you go to the formula sheet, section 1, delta X equals V average times the time. Because the cannonball never speeds up or slows down horizontally, V average equals V initial equals V final equals V at any other point in between. So whichever way you want to get this anyhow, distance equals speed times time if you're keeping a constant velocity. And fill in the numbers. V initial X is the 100 meters per second times 4.95 seconds. Roughly half a kilometer away. Well, let's do one more, just so you don't get the idea that these questions always have to ask for how far away does it land. I'm going to point you at that again. This is actually a continuation of number 2. I suppose I could have made it part A and part B, but kind of like Newton with his first 2 laws that are really the same thing. I made this example number 3. So same cannonball. This time the question is, how fast is it going when it hits the water? So the word speed, if you're talking about average speed and average velocity, things can get a little more complicated. Like that example I did once with a school bus that goes out and turns around. But when you're talking instantaneous anyhow, in a delta t that's approaching 0, there is no time for a school bus to turn around and go back. In the instantaneous case, which is usually what you're talking about, the word speed means the magnitude of the velocity vector. And as I've already mentioned, the way you get the magnitude of a vector from its components is from the Pythagorean theorem. If you want to see the picture that goes with that one more time, as the cannonball reaches the water, it's going in something roughly like that direction. So there's its velocity vector, V final. So there's the y component, there's the x component. They make a right triangle with the final velocity on the hypotenuse. So we need to figure out each component of the final velocity and then stick them in that, except we don't need to figure out the final x component because we already know it, because the x component never changes. If the initial velocity, if the sun was directly overhead, got the shadow going along the surface of the water. If that was originally going 100 meters per second, it's still going 100 meters per second in the end. So Vx is constant. 100 meters per second throughout the entire flight. As for the y component, well, actually, there's a couple of different equations you could pick, and you could solve for v final out of either one of them. I went with back in section 1, it says v final equals v initial plus at, and I stick y subscripts on everything. And now, if the sun is right on the horizon, that's talking about the shadow that's coming down the front of that cliff. The initial velocity in the y direction, back over here in my table again, it starts out, the shadow on the front of the cliff starts out with a velocity of 0 as the ball first emerges from the cannon, and then it falls faster and faster after that. So v initial is 0, acceleration the shadow is a freely falling object, even though it's not really an object. And I had, back over here, I had figured out the time as I was going along through number 2. So I'll stick that in for t. So x component, y component, stick them in the Pythagorean theorem. Of course, the minus sign disappears when you square it, so there wasn't really any point in writing it down in the first place, but well, I suppose we all do a lot of things that don't really have any point, don't we? But let's not get too philosophical. Let's just punch up the numbers and notice that they come out 111 meters per second. That's how fast the cannonball is going as it reaches the water. And of course, the importance of that number is that's the one that determines how much damage this can do to something it runs into. The faster it's moving, the harder it hits. So this right here is the borderline between one topic and the next. And let's see, what else is in here? Yeah, this is a good place to divide it up between the first recording and the second one. So when I turn the camera back on again, which I plan to do in about 30 seconds actually, we'll look at motion in a circle instead of a free falling object, something going around in a circle at a constant speed.